Dimensions, the fabric of reality, the very essence of how we understand and interact with the universe. We perceive the world around us in 3 dimensions. These dimensions shape our daily experiences and interactions. These dimensions are length, width, and height. They are fundamental to how we measure and understand space. They define the space we live in and the objects within it. Every object we see and touch exists within these 3 dimensions. A point has 0 dimensions. It represents a precise location, but has no size, area, or volume. A line has 1 dimension. It extends in a single direction, having length but no width or height. A square has 2 dimensions. It has both length and width, forming a flat shape. A cube has 3 dimensions. It possesses length, width, and height, creating a solid object. Imagine a tiny ant crawling on a piece of paper. To the ant, the paper appears as a flat 2-dimensional surface. To the ant, the paper appears as a flat 2-dimensional surface. It can move forward, backward, left, or right. It can move forward, backward, left, or right, unaware of the dimension of height. The ant's world is limited to 2 dimensions. Now picture yourself holding a pencil above the paper. From your perspective, you can see the entire surface. From your perspective, you can see the entire surface, including the ant's limited world. You have a broader view. You experience an extra dimension height that the ant cannot perceive. This additional dimension gives you a different perspective. This example illustrates the concept of dimensions. Each dimension adds a new layer of complexity and understanding. Each dimension adds a new degree of freedom, expanding the possibilities of movement and perception. As we explore higher dimensions, our understanding of reality deepens, revealing the intricate fabric of the universe. Beyond 3 dimensions. Introducing the 4th dimension, a concept that stretches the boundaries of our understanding. Our brains are wired to understand a 3-dimensional world, where we perceive height, width, and depth. But what if there were more dimensions beyond our perception? Imagine a reality that extends beyond the familiar 3 dimensions. Physicists have long grappled with the concept of higher dimensions, exploring theories that challenge our conventional views. One of the most intriguing is the 4th dimension, time. Time is not just a measure of moments passing by. Unlike the spatial dimensions, time behaves differently. It is a continuous, ever-moving stream. We cannot move freely in time like we can in space. We are bound to experience it in a linear fashion. Time seems to flow in one direction, from the past, through the present, to the future. This unidirectional flow shapes our existence. While we cannot see or touch time, we experience its passage. It is an invisible force that governs our lives. We see it in the aging process, the changing seasons and the cycles of nature, and the movement of celestial bodies. The stars and planets follow the rhythm of time. Time is a fundamental aspect of reality, as real as the 3 spatial dimensions. It is the thread that weaves the fabric of the universe. Time, the unseen dimension. Time is often referred to as the 4th dimension. It is intertwined with the 3 spatial dimensions, forming a unified fabric of space-time. Every event in the universe has a specific location in both space and time. Imagine a meeting you have scheduled. To pinpoint this event, you need to know not only where it will take place, its spatial coordinates, but also when it will occur, its temporal coordinate. This interconnectedness of space and time has profound implications for our understanding of the universe. It means that our perception of time is not absolute, but can be influenced by factors such as gravity and motion. Einstein's revolution, relativity, and time dilation. Albert Einstein's theory of relativity revolutionized our understanding of time. He proposed that time is not absolute but relative. It can be stretched and compressed by gravity and motion. One of the most mind-bending predictions of relativity is time dilation. Time slows down for objects moving at high speeds or experiencing strong gravitational fields. This means that time is not a constant, but a variable, dependent on the observer's frame of reference. Imagine 2 identical clocks, one on Earth and one on a spaceship, traveling at a significant fraction of the speed of light. According to relativity, time would pass slightly slower on the spaceship compared to Earth. Section 5. Time's fickle nature. Real-world examples of time dilation. Time dilation is not just a theoretical concept. It is a fascinating phenomenon that has been observed and measured in various real-world scenarios. It has been experimentally verified and has practical implications for technologies we rely on every day, such as the Global Positioning System, or GPS. For instance, GPS satellites, which orbit Earth at high speeds and at high altitudes, experience time dilation due to both their velocity and the weaker gravitational field compared to the Earth's surface. Their internal clocks run slightly faster than clocks on Earth's surface. This difference, though minuscule, accumulates over time and can lead to significant errors in positioning if not corrected. To ensure accurate positioning, GPS systems must account for this discrepancy by adjusting the satellite clocks to match the time experienced on Earth. Astronauts aboard the International Space Station also experience time dilation, albeit to a lesser extent. The combination of their high speed and the reduced gravity in orbit causes their time to pass slightly differently. When they return to Earth, they are slightly younger than they would have been if they had stayed on the ground. This effect, while small, is a real and measurable consequence of time dilation. These examples demonstrate that time is not a rigid, unchanging entity, but a flexible aspect of the universe, influenced by gravity and motion. The more we understand about time dilation, the more we can appreciate the intricate and dynamic nature of time itself. Section 6. A fifth dimension, Kaluza-Klein theory, and beyond. The concept of higher dimensions extends beyond the four we experience. Some theoretical physicists propose that additional dimensions, curled up and hidden from our perception, could unify the fundamental forces of nature. One such theory, Kaluza-Klein theory, suggests a fifth dimension, curled up into a tiny circle at every point in space. This extra dimension could potentially unify gravity and electromagnetism, two of the four fundamental forces. While Kaluza-Klein theory has its limitations, it paved the way for string theory and other theories that explore the possibility of extraspatial dimensions. Section 7. The Block Universe, a frozen river of time. The concept of time as a dimension raises intriguing questions about the nature of reality. If time is a dimension like space, does that mean the past, present, and future all exist simultaneously? The block universe theory suggests just that. It proposes that the universe is a four-dimensional block, with all moments in time existing at once. Time, in this view, is like a frozen river, with all events, from the Big Bang to the end of the universe, laid out along its course. This deterministic view of time challenges our intuitive understanding of free will and the passage of time. Section 8. Imagining the fourth dimension. Analogies and thought experiments. Visualizing higher dimensions can be challenging. Analogies and thought experiments can help us grasp these abstract concepts. Imagine a two-dimensional being, flatland, living on a flat surface. It can only perceive objects within its two-dimensional world. Now imagine a three-dimensional sphere passing through flatland. Flatland would only see a series of circles, appearing and disappearing as the sphere intersects its plane of existence. Similarly, we, as three-dimensional beings, may only perceive shadows or projections of four-dimensional objects. Another helpful analogy is to think of time as a loaf of bread. Each slice represents a moment in time. The entire loaf encompasses the past, present, and future, coexisting within the block of space-time. Section 9. Time travel. Fact or science fiction? The possibility of time travel has captivated the human imagination for centuries. While time travel remains a staple of science fiction, is it scientifically plausible? Einstein's theories suggest that time travel may be possible, at least in theory. One proposed method involves wormholes, hypothetical tunnels connecting different points in space-time. Traveling through a wormhole could potentially allow for shortcuts through time, although their existence remains purely theoretical. Another possibility is time dilation. By traveling at speeds approaching the speed of light or experiencing extreme gravitational fields, time could slow down significantly, effectively propelling travelers into the future. Section 10. Paradoxes and possibilities. The implications of time travel. The prospect of time travel raises intriguing paradoxes and ethical dilemmas. One classic example is the grandfather paradox. What would happen if you traveled back in time and accidentally killed your grandfather before your parent was born? Would you cease to exist? Or would the timeline split, creating an alternate reality? These paradoxes highlight the complex implications of tampering with the fabric of time. If time travel were possible, it would raise profound questions about free will, causality, and the nature of reality itself. Section 11. Conclusion: the ever-evolving mystery of time. The fourth dimension, time, remains one of the most profound and enigmatic concepts in physics. From Einstein's revolutionary theories to the mind-bending implications of time travel, the nature of time continues to fascinate and challenge our understanding of the universe. While the mysteries of time are far from fully unraveled, our ongoing exploration of this elusive dimension deepens our appreciation for the intricate workings of the cosmos and the profound interconnectedness of space, time, and reality itself. As we continue to probe the boundaries of physics, we may one day unlock the secrets of time and its role in shaping the universe we inhabit.